Hello everyone. So in this recording, I'm going to talk about lecture 13, which covers part of chapter 12. Last time we talked about local area networks, and I mentioned, of course, the main example is the Ethernet, and I mentioned the shared medium. So today we're going to talk about um, the methods of access the or how the nodes share the medium, right? Which we introduced last time. So with this in mind, the first mechanism that nodes used to share a common medium was a system that was named Aloha, right? And the Aloha was the grandfather of all of these techniques. In the Aloha, which is a system that used to connect universities or university campuses in Hawaii, right? There were many islands, campuses spread over multiple islands, and they want to communicate with each other. So they created this Aloha system. So for the Aloha system, what happened is every um, island has a wireless tower, and to send information, they divide the data into packets, and they send the packet. One tower sends the packet to the others, right? And as we talked about last time, what happens is if the packet was destined to the destination, it will read it. If not, it will not. It will ignore it. So it was a broadcast system, right? And of course, sometimes the packet or frame get corrupted. So it was using something similar to the stop and wait. So the packet is sent, then the transmitter waits for a reasonable time. So if the propagation time is 2 seconds, so it waits for 4 seconds, 2 seconds to transmit the packet and 2 seconds for the acknowledgement to arrive, plus of course the time we need to transmit the frame itself. So okay, we wait a reasonable time. If the acknowledgement doesn't come, we assume that the packet or the frame was corrupted, and we send the same frame again, right? Simple stop and wait. Um, so how do we detect the error? By something like the frame check sequence or the CRC at the end of the frame. Now, because it's a shared medium, sometimes the signal gets corrupted for other reason than the noise. And one of them is a collision, right? It is possible that multiple towers decides to transmit a packet at the same time. So what happens is midway they will collide and the signal is corrupted and nobody receives anything, right? Or they receive the frame corrupted, so nothing happens. So in that case, while the transmitter waits for a specific amount of time, same as before, no acknowledgement comes, so it waits and then retransmits the packet again, and hopefully this time will go through, right? The technique wasn't perfect because it is possible that the packet will get collided again with another frame because there was no coordination among these towers. Each one of them, each transmitter will send wherever they have a frame to send. Right? So the first improvement to the Aloha system was to decide that instead of leaving the transmitter to send whenever they like, how about we synchronize the time? So we divide the time into slots, and then each uh, transmitter will transmit only at the beginning of the time slot, right? So what I mean by that, let's say um, you can only send at the beginning of the second, right? So you can, let's say now it's 8:17 and 15 seconds. And then you wait, if you want to send something, you wait until the start of the next second. So 8:17, 8:17 and 16 seconds, right? So only send at the beginning of the second. So what happened is, right? So if we have the time divided this way, and we have, this is the 10th seconds, this is the 11th second, this is the 12th second, and so on. The actual time slot depends on how long it takes to send the frame, right? So if the frame time takes half a second to send, then the time slots is divided half seconds each, right? Rather than seconds. But anyway, it doesn't matter. We'll just call them time slots. So if station A and station B and station C wants to transmit, they will transmit only at the beginning of this slot. All right, so what happens? They noticed that actually this system improves the utilization of the channel and decreases the number of collisions. Why? Because if A and B decide to send earlier, before the time slots system introduced, if A and B wants to send, let's say A sends first, right? And B, after a while, it decides to send. So it will send here. So there is an overlap, right? So they will collide and both frames will be lost. In this new system, if A sends first and B wants to send, right? Let's say B has a frame that was ready to send here in the middle of the time slot. It doesn't send it right away. It waits for the next time slot to begin and then send it. So now there is no overlap between these two frames and no collision happen and the packets arrive correctly at the destination. So here we eliminated not all collisions, but we eliminated a big number of collisions. Still, C, for example, may have something ready at the same time as A, so they will send at this time slot. So now these two will collide because they happen to be sent at the same time and both will be lost, right? So the system does not eliminate all collisions, but because we are dividing the time into slot, we eliminated the collision that happened, a partial frame. So now the collision either happened for the entire frame, right? So all the frame is destroyed, or it doesn't happen. So and that improved or almost doubled the utilization. So maximum utilization for the Aloha system was 18%, and that doubled to 37%. All right. The Ethernet, which is a wired, not wireless, so Aloha was wireless, but with the Ethernet, took that system and used it with proper modification for the fact that we are using wired. So for wired systems or wired media, instead of, well, of course, it's guided media, so we have a bus and we have these nodes connected, right? So as I said before, a frame is sent, right? and it propagates along the cable here. So at some point after certain propagation time, all the nodes will hear about it. The Ethernet relies on a feature or a fact that the propagation time, right, the time that takes from one end, the maximum propagation time, the time that takes a bit to travel from one end of the bus to the other end of the bus, is very short compared to the frame time. So the frame time is actually much longer, the TF, compared to the TP, right? So if a frame was sent by node A, for example, to node F here, right? The frame itself will occupy the entire bus. Right? So this means that all other nodes will hear it, right? It will take a very short time to reach the end, and for the entire TF time here, all the nodes will hear it. So because all the nodes will hear it, they will not send something. So what happen is they will try to read the medium first before they send anything. If they read the medium and they see that there is traffic on the medium, there is some packets going on, right? And remember last time I said everybody will read the packet to decide whether it's for them or not. So they know if there is transmission. If they know there is transmission, they don't send. So that's what we will call the carrier sense multiple access system. So the carrier sense refers to the fact that the nodes will listen, they will sense the carrier. The carrier is you know what the carrier is. So we'll talk about modulation. So we have the carrier signal, right? So if they detect the signal, this means that there is transmission going on. So they know there is a packet going on, right? So they will wait for the carrier or the bus to be idle before they send something. So that will reduce the amount of collisions, but it doesn't eliminate the collisions immediately or completely. How or why it doesn't eliminate the collisions immediately? Let's talk about, two nodes here, A and B, right? And let's say that A is sending something. So A starts sending. And the propagation time is small, but it still takes time. B, unaware of A is sending anything, so it starts sending as well. So B did not hear any medium at that time because the signal still didn't reach it. It will take up to this time to reach, right? But it's still in the middle. So the signal did not reach. So A listened to the medium and said, okay, there is nobody else is sending, so I'm going to send as well, right? So it starts sending its signal. So the signal coming from here and the signal coming from here, they will collide at some point. And that is a collision. So two frames being sent from two parts of the medium, A and B, right? And because there is some propagation time required, so the signal may not instantaneously be heard on another or at another station. So that other station may think that the medium is free and start sending, right? So that happens. And that's why we need to, one, make the frame propagation time small, right, compared to the frame time. And how do we make it small? By limiting the bus length. We limit the cable length. And I mentioned last lecture that we have a limitation of how far the cable goes. And one of the reasons is so that we can control the TP. Another thing that we notice is we need to make sure that the frame itself has a minimum size, right? So we need to make sure that the frame is longer than the TP. So the frame also has a minimum size. And the frame, I think minimum size, maybe I don't remember accurately, but I think it's 64 bytes, right? So refer to your book to get an actual number, but it has a limited, it has, like, we cannot send a frame shorter than that size. The reason for that also because we need to make sure that the TF is greater than the TP. Okay, so let's go back to some of the details. So we learned that we need to listen first and then send. By the way, listening first in the wireless. Um, so Aloha did not listen first and send. It's more difficult for wireless to do the carrier sense, right? It's easier for the wired medium to do the carrier sense. So that's why we don't. Um, it wasn't there in the Aloha system. Right? All right. So what happens if there are collisions? So in that case, as we saw here, we have a collision. The collision itself, it will travel. So these dotted lines means that the collision happened at some point, but the signal will continue to travel, corrupted, but still continue to travel. So at some point, B will hear the collision and A will hear the collision. They will both know that a collision happened. So what they will do at that time is each one of them will start counting specific time, random time. So if they start sending immediately after, they will have a collision again, right? So instead, they will wait random amount of time. So you don't know how random. It may happen that B weights less than A, and now A sends its packet. A is still waiting, but once A hears the packet coming from B, it doesn't transmit anymore because now it knows that the bus is not idle, it's busy, so it waits until the the medium is free again or idle again and then starts to transmit. So now in your textbook, you have multiple variations of how, like, this time is managed, or how the idle is time is managed. So sometimes is A waits until the packet is totally transmitted and the idle the the medium is idle and transmit immediately. Well, that's problematic because there may be another node C that also hears the frame coming from B and waits until the bus is idle and starts to send. So if A is waiting and C is waiting, both of them are waiting, and immediately after the bus is idle, they will start sending, there will be a collision. So we will have certain variations of whether we wait for there is a probability, right? So there are probabilities. Instead of A guaranteed to send immediately, it may send with a probability of 0.1 or probability of 5%. Or so that probability means that if there are multiple stations waiting for the idle time to happen, they don't send immediately. Some of them will send, some of them will not, right? So you have variations of what the probability is. And also what happened after the collision, right? So you have variations as well of about the reaction of the stations after collisions. So you'll see here, this is a repeat of what I just said. To reduce the waste of capacity due to collisions, um, uh, the carrier sends multiple access collision detection. I didn't talk about collision detection yet, or actually I did, about detecting the collision. That's why um, we stop transmitting. But if here we see if the medium is idle, we transmit. If the medium is busy, then we listen to the frame until it's over, and then we transmit immediately, right? So, and as I said, there are variations of the system where the transmission happen with probability, not immediately, right? And then um, here is the situation that explains the CD, the carrier detection part. So if a collision is detected during transmission, we send a jamming signal, right? So this is the part that is different from what I mentioned here. So here I said that A and B wait for they receive the collision, so they wait for a random amount of time and then they try again, right? The the CD part that was added, it's actually instead of just waiting like passively until um, un, for a random amount of time. No, instead they will start sending, as soon as they detect collision, they will start sending a jamming signal. So let's make this look like a jamming signal here, right? So they will send the jam. Everybody who detects the collision sends a jamming signal. Jamming signal just noise or a specific signal that was designed to tell everybody stop doing whatever you're doing because there is a collision. The reason for that is to inform maybe A and B detected the collision, but F here didn't detect it yet because it's further away. So by sending the jamming signal all the way, everybody detects it, so nobody tries to send anything. And then they will continue doing the waiting as we said before. So the waiting follows a binary exponential back off, right? So it's not just, I said it's a random time, but the random time doubles, right? So what it means by double. So let's say um, after the first collision, um, each station will choose to send something between 1 and 10 seconds, right? So randomly, they will wait between 1 and 10 seconds. The next time, if they transmit and the collision happen again, next time they don't just pick a random number between 1 and 10. No, they will pick a random number between 1 and 20, right? If the collision happens for the second time, they will pick a random number between 1 and 40. So the random number that they will pick, it's becoming exponentially, it increases up to a certain point, up to 16 times I think. uh, and then at that time, after they try multiple times to send and nothing happens, they stop. and they informed the upper layers. The Mac informed the upper layers that it couldn't send a packet. Maybe there is a problem with the network, right? So they will give up. And the same thing with the Aloha. After they try multiple times, if it doesn't happen, they will just say, there must be something else, we give up, right? So it may be the channel is too busy, too many nodes connected, or if there is a physical problem with the connection itself that it doesn't allow the signal to propagate, or any other reason. Right. So this is what I explained here, just in a different format, right? So there is a transmission and there is a collision that happen when the two transmission overlap. So there is a collision, and that collision will travel, same as the rest of the signal will travel, and nodes will hear it eventually. All right, so we have multiple so go back to the textbook and see how there are several variations of the carrier sense multiple access with collision detection. So read about those, but the principles are the same. So Ethernet, as I mentioned last time, was there for a long time, and it started as a bus, physical bus topology, and then it became logical bus, which means that we can build a star topology, but it still acts like a bus, right? So instead of a bus like being a long bus, we can just make it short as treat it like a single point in a hub, right? The among the first standards was the 10 base 5, and the 10 refers to the 10 megabits, which is the maximum speed at that time, and the 5 and the 2 here refers to well, in my mind it refers to the thickness of the cable, but it could be something else. So the 5 was what's called thick cable, and it was a coaxial cable, and it allowed the maximum segment length of 500, and you could connect up to 4 repeaters. So those are not exactly bridges, but repeaters that can extend the signal, right? So you can come up with 2 kilometers of cable. Now, that doesn't mean we build a network that's 2 kilometers long, but we could run the cable around in a building, so it takes a long time going back and forth, especially if you are connecting everything in a bus, in a daisy chain. And you can connect up to 100 nodes to this bus. Signaling technique, you have seen this before, so that's a baseband, Manchester, and the cable diameter was 10 millimeters. So that's why it was called thick cable, because it was heavy, and it was imagine 500-meter with a cable that is 1 centimeter thick. So handling this cable needs sometimes a forklift. The next variation made the cable thinner, which is more convenient to handle, and it was called 10 base 2. The maximum length was 185. I think last time I mentioned it wrongly, that was 120 or 130. It's actually close to 200. The nodes, maximum nodes, 30 per segment, and it's just 5 or half a centimeter thick, right? And those cables, the 10 base T were common. The common was orange, and the 10 base T, the common color was black. And I remember that because when I first started working long time ago, I have seen both of them, and I didn't work on the orange cable, but I worked on the thin cable. And very shortly before the technology became obsolete and I didn't work on it anymore, right? But I remember that was early 90. 10 base T came after, and the T was for, I think, for twisted pair, and that the technology that allows the star topology. So here we have a bus, and then we started doing star. So this cable is no different than the cable that you see nowadays. So it is just a thin cable, flexible, that you can connect, and you can connect it using a star topology. So you have a hub, and you connect a cable from the hub to the station. The limitation was 100 meter. So from the hub to the node, or maximum 100 meter, right? And this limitation continues until today. All Ethernet cables, twisted pair or unshielded twisted pair Ethernet cables have a limitation of 100 meters. And then we have fiber cable. The fiber cable, so 850 nanometer, that's a multi-mode fiber. And the multi-mode fiber allows you to build a star topology, but the length can go up to 500 meters. So you can have a segment of 500 meter, or you can have a node that's far away from the hub, like 500 meter far away from the hub. Here we can have up to 1024 nodes. Here we have 33. So why would I put 500 meter node away from the hub? Well, think about, we talked about hierarchy last time. So you could have a hub that is connected to another hub. Right? So this could be in one building, and this is another building, and that's 500 meter in between, right? You have to be careful, however, that the maximum distance has to be 500 meters. So if this is 100, so this could be 400 meters. So you have sometimes these limitations. You have to look into the specifications carefully to see what the maximum distance is. Like, is it end to end, for example, or is it the total length? So we will see when we get to the design course that we have to consider end-to-end length, and there are limitations of the distance. Maybe you will encounter that even before in another course. After the 10 megabits per second specification came what is commonly known as the fast Ethernet. So the fast Ethernet allowed 100 megabits per second. And there is no coaxial anymore, so it came with twisted pair or fiber. So the T is for the twisted pair and the F is for the fiber. And we can have two kinds, shielded twisted pair or unshielded twisted pair. So the unshielded is usually cheaper. And most of the specifications from now on, they are the same. So they keep the data rate, they keep the maximum segment length, the network span. So the network span, these end to end, this is what I was talking about. So if you have a hub here, So you have a node and node. So this is 100 and this is 100. So the distance end to end is 200, right? So these are the things that you have to be careful about. We don't have to worry about them in this course, but later on. Then we have the fiber variations. This is the signaling technique, by the way. So that's 4B, 5B, and this is the non-return to zero inverted and all of that. Network span here is 400 meters and here is 200 meters. This one actually, this is the fiber. This is a twisted pair, but instead of 2 pair, we have 4 pair. So the cable itself, this is a 2 pair, means that we have a cable that has 2 or 4 lines, right? So one for transmission, one for the reception, and the 2 for the ground for each one. So we have 2 wires, one pair for the transmission, the other pair for the reception. Here we have 4 pair. What is the pair for? What are they? They divide the signal actually into 2 parts, and so they go over multiple wires instead of just 2. We will see category 3. So now the common things that we see nowadays is the category 3 or 4 or 5, okay? And they need more wires. And yeah, so it says here that it's a lower cost alternative. So the traditional Ethernet came as half duplex because we cannot send and transmit at the same time. But when switches were created and we were able to put one node per port, right? So now we don't have to share the medium. We really don't. When we create when this is replaced by a switch, which is a bridge with multiple ports, right? So, and we have a dedicated segment for each node. So we don't have the possibility of collisions. That we always talk between the node and the switch, right? Between the A and B and the switch. So that actually allowed for having a full duplex communication. So we can have 2 channels, one for transmission and one for reception. And as I mentioned earlier, we can have 2 pair or 4 pair. So that's allowed us to have 2 channels, each one using a different set of wires, right? So with the fast Ethernet, we started to have a full duplex operation. Before that, with the 10 meg Ethernet, we couldn't, right? So if you see 10 meg Ethernet means that works only half duplex. All right. Also, if you are using a hub, you cannot use full duplex. Luckily, you won't see a hub anymore unless you are working on a really ancient network. So when you have 100 meg going in and 100 meg coming back, that's theoretically you have 200 megabits per second bandwidth available to you. It doesn't really mean exactly 200, but that's at least the theoretical maximum, right? If you are constantly sending packets and constantly receiving packets at the same time, right? So a theoretical limit. could be 200. Um, so here it says you must use switching hub. It's actually must use a switch, right? So I think this is what the book means. A switching hub is a switch because there's no a hub is a hub, so it means a switch here. Um, no collisions, as I said. The carrier sense multiple access with collision detection algorithm is no longer needed. Why? Because there is no need for shared medium anymore. Right? If you look at this picture, now we have point-to-point connections. Point-to-point connections between the switch and the node, so there is no shared medium. Anything that A sends, it can put it immediately on the line and it receives the switch. Anything the switch would send to A can put it immediately on the line and it reaches A. And because the transmission and the reception happen on two different lines, there is no possibility of collision, right? With a single with a half duplex, it's still the possibility of collision between the two nodes because they may try to send each other packets at the same time. But of course, because there are two nodes, only possibility of collision is limited. But with the full duplex, we don't really need the carrier sense multiple access collision detection anymore. Okay. It's still there in the standard for compatibility reasons, for backward compatibility, but you don't need it. So you can still continue using the carrier sense multiple access with full duplex and 100 meg. Now that was eliminated completely when the gigabit Ethernet was introduced. So when we added gigabit, actually now you don't have a choice. You have to use a switch, and there is no carrier sense multiple access anymore. So you cannot have, even if it's available, you cannot have a hub with gigabit Ethernet. Now, obviously, gigabit Ethernet means that we are sending at 1000 megabits per second. Now, with this came a little bit of a challenge. Remember, one of the fundamentals that was used to build the Ethernet is we need the TP propagation time to be much smaller than the TF. But that was in the days of the 10 meg. When we introduced the 10 meg, the 100 meg per second Ethernet, well, that was shortened by 1/10, right? So whatever frame we're sending, if it took 10 seconds to send, 10 seconds is really eternity in network time, but let's assume it's 10 seconds. If we increase the speed by 10 times, we will decrease the time, the TF time, by 10 times as well. So the 10 seconds become 1 second. If the speed is becoming 1 gig, now the 1 second become 0.1 second to transmit the frame. So at some point, the TF becomes smaller than the TP. Right? So it may take only this much to send the frame. Propagation time we cannot control, it's physics, right? And it depends on the distance of the cable. So that's problematic in some cases. So to make sure that the TF is still relatively bigger than the TP, we or they introduce they add they do pulse stuffing or simple stuffing to the frame, so they make it um, equal to 4096 bit times, right? So instead of 512 bit times in the days of the 10 meg and the 100 meg uh, Ethernet, now it's increased to 4 kilobits, just to make sure that TF is a little bit bigger. I am not quite sure at this point is why do we need that if there is no possibility of collision. So uh, go read the textbook. Maybe there's a hint for that. I don't really remember. Um, but I think it's a good thing to look at, because I don't know why we need to make sure that TF is longer if we are not relying, or if we are not using collision detection anymore. Anyways, the other thing the standard adds to take advantage of the speed is something called frame bursting. So one of the things that we still need to handle, even without the carrier sense multiple access, is still Ethernet as a shared medium. Right? So still packets will send traffic at random times, and they will share the medium somehow. So even if that medium is actually, you know, uh, the switch itself in this case, to take advantage of the short frame time, we could uh, concatenate multiple frames and send them like a train, right? So instead of sending one frame at a time, we could do frame bursting. So the node sends multiple frames uh, without um, without waiting, right? And that improves the performance. So and then of course we have the 10 gig, which is common nowadays. The 10 gig, almost every switch, well, not almost, but a lot of switches that you buy today, they have at least few ports that have 10 gig ports. So the 10 gig ports have we now have something called 10 gig 10G base S. That's for um, uh, the multi-mode fiber, and the L is for single mode fiber with the um, the wavelength is 1310, and the other wavelet is 1550, is also single mode fiber, but the difference is this will give you a longer distance. And actually, the standard specifies L and E, so L give you up to 10-kilometer distance, E gives you 40-kilometer distance. The industry actually have something that's not part of the standard, but the industry nowadays you can buy uh, you can propagate the Ethernet signal up to 100 kilometers. Right? It is possible to do that. To do that, you have to have a laser, right? So the fiber in general needs to have a laser. So just so that you are aware of it, so there is something called SFP, and I'll give you the picture without actually explaining too much, but something like this. Right? And this is a laser module. So actually, this is not a laser. Let's see, something that's actually laser. Here, something like this. So the LX, LH, that's for the LX that I didn't mention yet in the back, but this is laser. So you need this to be plugged into the switch, and on this side here you will have the cable, the fiber cable. The fiber cable themselves are single mode fiber. See, Google knows what you're talking about. So this is a fiber cable. This is short distance fiber when you're talking about long haul. So all of these are short distance. When we talk about something like let's instead of a video, let's have just a picture. So something like this will go into kilometers of distance, right? Now I want a picture and the good picture doesn't appear. But anyways, so the fiber can be used inside a building or it could be used between cities. So when we have 100 kilometer or even 40 kilometer of connection, that's a long distance, right? And it needs a special installations. And that actually, with the 1 gig and the 10 gig Ethernet, the Ethernet became not a LAN technology. We talked about Ethernet so far as a LAN technology, local area technology. But when you are able to connect two buildings across two cities, now the Ethernet is not really a local area network technology anymore. So one of the reasons for the Ethernet success is we can use it for everything. We can use it to connect a building and we can use it to connect multiple buildings. And I can actually, there were some networks that I managed that extends across multiple cities in Nova Scotia here. So there are kilometers and all Ethernet. So the last, so we talked about LE, and this the LX4. Um, it's a single mode fiber or multi-mode fiber or two different kinds of multi-mode fiber. So that is good for either inside the building. So you saw the yellow cables or the bluish cable. So the yellow cable usually is single mode and the bluish cable is multi-mode. So they are good for connection inside the building. And you can also use the same technology to connect up to 10 kilometers. So when we use 10 gig, we can, of course, use it to connect nodes to switches or switches to servers. So any type of connection will work. We are actually now going into the available now is 100 gigabits per second, and that is really now it becomes the realm of the wide area network. So we need this bandwidth, this much bandwidth to connect between large data centers or between large infrastructures. So the Ethernet allows us to do that as well. Now it's not written here, but if you notice that we went in the speed by increasing the speed 10 folds each. So 10, then 100, then 1,000, then 10,000. So that's the 10 gig. And then the 100. Right, so So that's the fast Ethernet, that's gig, that's 10 gig, that's the 100 gig. At some point, you will see that there's a lot of, inside a small network or even medium-sized network, um, you may have a reasonable use for the 1 gig, right? And even a reasonable use for the some. So you can build a network that has switches. The switches themselves connect to nodes like your laptop or your printer or workstation or camera, and that could use 10 gig or 1 gig. 1 gig maybe reasonable to connect switches together, because now you have 1 gig, 1 gig, 1 gig coming from multiple nodes. So you want to send the traffic to another switch. So maybe you need to have 10 gig to connect multiple switches together, right? So that will be an uplink, right? Uplink is between a switch and another switch, or a switch and a big server. But there is a gap here. Not all nodes need to jump. Let's say you have a wireless wireless access point here. 1 gig may be too little, too small, because it connects to a lot of nodes, but 10 gig is too much. So the Ethernet Standard Committee noticed that there is a gap in, like, we have to jump from 1 gig to 10 gig. 10 gig may be too much, and 1 gig may be small. So they actually started doing, or now there are available the standard of 2.5 gig Ethernet and 5 gig Ethernet, right? And also between here and here, we have a standard, the 40 gig Ethernet, right? So 40 gig Ethernet is very common for data centers, because 100 gig is too much to connect servers, but 40 gig is reasonable to connect large servers, especially when we have virtualization. So the hardware itself includes a lot of virtual machines. So that's common. And this is common to connect between switches, or from a switch to a heavy camera, for example, or a wireless access point. So they are filling the gaps in speed. So we have a technology that is really versatile. It goes from 10 megabits per second up to 100 gig, distance-wise from 100 meters to 100 kilometer. It is not really a local area network anymore, right? So when you look at the uses of the Ethernet. So one of the very successful technologies. All right, so that's bring us to the end of this lecture. Thank you, and I'll talk to you in the next recording.